Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over the calculating of entropy for changes in state. So we're going to calculate how to find the entropy change for changes of state. So we have to go back and remind ourselves some terminology we need to know. So remember, the system that we're going to be looking at it's usually going to be the reaction or the substance that's undergoing the change. So in this case, we're looking at the substance that is undergoing the change. That's going to be our system. And then the surroundings is the rest of the universe, the air, the water, whatever's out there. That's going to be the surroundings. And so, keeping in mind that whenever we change, whenever we have a change in state, this is going to be accompanied by an exchange of energy or heat in between the system and the surroundings. So if you're going from a liquid to a gas, that's going to be the liquid is absorbing the heat. That heat is going into the energy of the molecules. That's increasing the kinetic energy of the molecules, the speed at which they're moving, the speed at which they're rotating, all of that. So that's going to absorb energy into the substance. And so the surroundings is losing heat, the system is gaining heat. Or if it's the opposite, if you're melting, um, no, excuse me, if you're freezing something or freezing water, for example, that means heat is going out of the substance. So the substance is losing the heat, and so the molecules are slowing down. The intermolecular forces are getting them to more strongly attract and come together. So got to keep that in mind. So we got the system and surroundings things going on, and we got this exchange of heat during the change of state. And so, bringing back to our attention this equation again, the equation is the entropy. Oops, excuse me. Sorry about that. So again, the entropy is S. S is equal to Boltzmann's constant multiplied by the natural log of W. And so remember, this is telling us that entropy is related to the distribution of energy among the particles. So remember W, the number of microstates, the number of ways in which you can arrange particles in an equivalently energetic way. That's being that we tied that before to this distribution of energy. So macroscopically, we can mathematically look at or calculate the change in the entropy of the system. So delta S is the entropy change of the system in this manner. So the change in entropy of the system is going to be equal to the amount of heat or energy that's exchanged for a reversible process. I'll talk about reversible processes in a moment. So it's the amount of heat exchanged during a reversible process divided by the temperature in Kelvin. And the temperature is constant throughout the process. So that means that the process has to be isothermal for this to be accurate, for this to be true. And so, again, this is the heat exchange with the surroundings in a reversible process. And so let's talk about the units a little bit here. So the units, if we're looking at our equation, the heat or energy unit is joules or kilojoules. In this case, it'll be joules, right? And so, and then the temperature is in Kelvin. So what this is telling us is that the change in entropy is a measure of the energy dispersal, like the amount of energy that's going into the substance, the system, or coming out of the system, going into the surroundings. It is a measure of energy dispersal per unit of temperature. So that's why we have joules per Kelvin. Okay, and so what is a reversible process? A reversible process is one that reverses direction upon an infinitesimally small change in some property. So an example would be like melting ice when the ice and the surroundings are both at 0 degrees, right? So when you're at 0 degrees, you've got some ice cube. The ice cube will be in equilibrium between melting and freezing. So it's on the edge as far as whether it's going to melt or not. So if you give it just a little bit of a push, for example, if I add just a little infinitesimally small amount of heat, I can get it to melt, right? Or if I take away an infinitesimally amount of heat, I can get it to freeze again. So this would be an example of something that is reversible. Okay, but if I have, say, for example, an ice cube, the ice cube is at 0 degrees. I put it on the counter at room temperature, which is 25 degrees. The ice is going to melt, and that's not going to be reversible because I can't reverse that process of melting by adding or taking away. In this case, I want to take away heat, right? But if I take away an infinitesimally small amount of heat from the ice or the water that's on the table, that's not going to reverse the process. The process of melting is still going to occur. So let's go through an example of how to calculate the delta S, or the change in entropy of a change in state. I'm forgetting my words. All right, so let's say we have melting water. So example here, I'll write the example here. So melting water at let's say 273 degrees, or Kelvin, I mean. So at a temperature is equal to 273 Kelvin. Okay. We need to know what the heat exchange is. So when you're melting water or melting ice, we need to know what the heat of fusion is, because that's going to be the amount of heat that's absorbed by the ice per mole. So it's kilojoules per mole. So we're going to have 6.02. So the heat of fusion for water is 6.02 kilojoules per mole. So that's Q. This is the Q that is absorbed, the heat that's absorbed by the ice to get it to melt. Okay, so then we have our heat of fusion. So that's going to be kilojoules per mole, right? So then let's say that we have 1 mole. Let's make it simple. We have 1 mole of ice that we're going to melt. So 1 mole, we have 1 mole of ice. So if we use our equation here, so delta S is going to be equal to the Q of a reversible process. So we're melting ice. And so the Q value is going to be, we're going to change this to joules because we want joules here. So this is 6.02 kilojoules. So if we change that to joules, that's going to be, let's say, 6,020 joules per mole. Right, but we're going to be multiplying that by 1 mole because we're using 1 mole. Okay, so then the moles cancel out because we have 1 mole of our substance. So that's going to give us the total amount of joules that we need to absorb for this amount of ice. And then we have the temperature, which is 273 Kelvin. And so then we can calculate that delta. We could calculate the delta S, or the change in entropy for this process of melting. And that comes out to, what I calculate this is 22.1 joules per Kelvin. So that would be the entropy change of melting 1 mole of ice. So I hope this was helpful. If you enjoyed this video, if you learned from this video, if this cleared things up for you or was helpful in any way, please like the video, hit that like button, share the video with your friends, subscribe to my channel, hit that notification bell up there so you can be notified by other videos that I put out, and also put a comment down in the comment section. Excuse me. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.